Every magnet you have ever held keeps the same strange secret. Snap a bar magnet cleanly in half, and you do not end up with a loose North Pole in one hand and a South Pole in the other. You get two smaller magnets, each with its own north and its own south. Cut those halves again, and it happens again and again. No matter how impossibly small you go, the two poles simply refuse to be pried apart. Yet electric charge plays by completely different rules. A lone positive charge exists. A lone negative charge exists. We isolate them every single day. So why does magnetism always, without exception, arrive in matched pairs? Some of the most respected theories in modern physics insist that somewhere out there a single, isolated magnetic pole must exist, and finding just one of them would force us to rewrite what we thought we knew about charge itself. If you enjoy following a genuine scientific mystery all the way down to its roots, a quick like or subscribe really does help this channel keep going. It only takes a second for you, but it makes a real difference on my end. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Pick up the nearest magnet. It might be a little black disc holding a photo to your refrigerator, or one of those silver bars from a science classroom. Hold it in your hand and feel that strange, invisible insistence as it tugs toward metal or shoves against another magnet. Now ask yourself a simple question that almost nobody ever asks. Where exactly is the magnetism coming from? You already know the answer in everyday language. A magnet has two ends. One we call the North Pole, the other we call the South Pole. Like poles push apart, opposite poles pull together. Every child learns this. It feels obvious, almost too simple to question. But hidden inside that simplicity is one of the deepest unsolved puzzles in all of physics. A puzzle that has haunted some of the greatest minds who ever lived. Because here is the thing. You can have just one of almost everything else in nature, but you have never, not once, in the entire recorded history of science, been able to hold just one magnetic pole by itself. Let me show you what I mean by setting two things side by side. Consider electric charge first, because electric charge behaves the way you might naively expect magnetism to behave. Rub a balloon on your hair, and the balloon picks up extra negative charge, while your hair is left with extra positive charge. Those two kinds of charge can be completely separated. The balloon sails across the room, carrying its surplus of negatives. Your hair, left behind, stands up carrying its surplus of positives. We can isolate a clump of negative charge over here and a clump of positive charge over there, and they exist perfectly happily on their own. The fundamental carrier of negative charge, the electron, is a real particle you can produce, store, accelerate, and count one at a time. Strip the electron away from an atom, and you are left with a positively charged ion. The two charges live apart. This is not exotic. It is the basis of every battery, every spark, every bolt of lightning. Electricity comes in two flavors, and those flavors can be pulled cleanly apart and kept apart. Now turn back to your magnet and try to do the same trick. The North Pole is at one end, the South Pole at the other. They feel like two separate things, the way positive and negative felt like two separate things. So let us simply separate them. Take a saw and cut the magnet straight across the middle, right between the two poles. Surely now you hold a lonely North Pole in one hand and a lonely South Pole in the other. Except that is not what happens. When you cut a bar magnet in half, you do not get a north piece and a south piece. You get two complete smaller magnets, each one stubbornly equipped with its own brand new North Pole and its own brand new South Pole. The cut you made to liberate a single pole instead conjured an entirely new pair out of nowhere. The face that was the middle of the magnet a moment ago has split into a fresh south pole on one fragment and a fresh north pole on the other. So you try again. You take one of those halves and cut it again. Same result. Two even smaller magnets, each with both poles intact. You cut again and again, growing more determined and more frustrated with every slice. The magnet keeps shrinking, but the rule never bends. Every fragment, no matter how tiny, comes out as a perfect little dipole, a two-poled object with a north and a south locked together. You could continue this until your blade is too crude to cut any finer, until you are down to a speck of iron barely visible to the eye, and that speck would still be a complete magnet with both poles. The single isolated pole you keep trying to create simply refuses to appear. It is as if nature itself is enforcing a law you cannot break with any saw. To understand why, we have to follow the cutting all the way down to a scale no blade could ever reach, down to the atoms themselves. Iron is magnetic because of what its electrons are doing. And here is the crucial insight that explains the whole stubborn behavior. The magnetism of an atom does not come from some little chunk of north stuff sitting next to a little chunk of south stuff. It comes from motion. It comes from electric charge moving in tiny loops. Picture an electron. It carries charge, and it behaves in two ways that generate magnetism. It has a property called spin, which you can loosely imagine as the electron behaving like a minuscule spinning ball of charge, and it also moves around within the atom. Whenever electric charge moves in a circle, in a loop, it creates a magnetic field. A loop of moving charge is the most basic magnet there is, and it is called a magnetic dipole. And this is the heart of the matter. A loop has no end. A loop is a closed path. When charge runs around a tiny circular track, the magnetic field it produces threads up through the middle of the loop, fans out around the outside, and curves back down to thread through again. It forms closed rings of magnetic field, like the field of a tiny bar magnet. One side of the loop behaves like a north pole, the other side behaves like a south pole, but they are not two separate ingredients. They are two faces of one single circulating thing. You can no more separate the north face from the south face of a current loop than you can separate the inside of a ring from its outside. There is no smallest piece you can break off that carries only one face. The two poles are not parts that were glued together. They are aspects of one indivisible swirl. Now zoom back out. A bar magnet is magnetic because, deep inside it, untold trillions of these atomic current loops are lined up, all pointing the same way, all their tiny norths facing one direction, and all their tiny souths facing the other. Stack enough of these microscopic loops in alignment, and their fields add up into the powerful field of the whole magnet. The north pole of the bar is simply the end where all those little loops present their north faces. The south pole is the end where they present their south faces. So when your saw slices through the magnet, it is not cutting between a region of pure north and a region of pure south. There is no such boundary. It is slicing through a stack of complete dipoles, and the moment it does, the newly exposed faces immediately reveal the two ends of the loops that were already there. A new north and a new south appear on the cut surfaces because those poles were never separate to begin with. This is why the trick can never work. Every magnetic object we have ever studied, from a galaxy-spanning field down to a single electron, gets its magnetism from these closed loops of moving charge. And a loop, by its very nature, always has two ends that come together as one. So now we can finally state the great asymmetry cleanly, in a way that should feel a little unsettling. Electric charge comes in two kinds, positive and negative, and you can have one without the other. A naked positive charge is a perfectly ordinary thing. A naked negative charge is a perfectly ordinary thing. But magnetism, as far as anyone has ever observed, only ever comes in matched, inseparable pairs. There is no naked north. There is no naked south. The universe seems to allow lonely electric charges, but forbid lonely magnetic poles. Why? Why should these two phenomena, which are otherwise so deeply intertwined, follow such dramatically different rules? That question is the doorway into everything we are exploring here. Before we go looking for that lonely pole, though, there is something you deserve to know about just how intimate the bond between electricity and magnetism really is, because it makes the asymmetry even stranger than it already sounds. Here is the secret that took humanity until the early 20th century to uncover. Magnetism is not really a separate force at all. Magnetism is what electricity looks like when things are moving. A magnetic field, at its very root, is an electric field seen by someone in motion. The two are not cousins. They are the same phenomenon wearing different clothes, and which clothes you see depends entirely on how you yourself are moving. Let me make that concrete, because it sounds almost too strange to be true. Picture an ordinary wire carrying an electric current, the kind of wire feeding any lamp in your home. Inside that wire, negative electrons are drifting along, while the heavy positive charges of the metal sit fixed in place. Crucially, there are exactly as many positives as negatives, so the wire as a whole is electrically neutral. It carries no net charge. Hold a stationary electric charge next to that wire and nothing happens to it, because a neutral wire exerts no electric pull. And yet, the moment that current flows, the wire produces a magnetic field, and a charge moving alongside it feels a force. Where did that force come from if the wire is neutral? The answer comes from Einstein, and it is one of the most beautiful ideas in all of physics. Special relativity tells us that moving objects are measured to be slightly contracted along their direction of motion, space itself squeezed for anything in motion. Now imagine you are a charge gliding along beside the wire, keeping pace with the drifting electrons. From your point of view, the electrons are the ones standing still, and the positive charges of the metal are the ones rushing past you. Because of relativity, the spacing of those moving positive charges appears contracted, crowded a little closer together, while the now stationary electrons appear more spread out. Suddenly, the perfect balance is broken. From your moving vantage point, the wire is no longer neutral. It carries a slight net positive charge, and that net charge produces a perfectly ordinary electric field that pushes on you. The force is unmistakably electric. But step back into the laboratory, where the wire sits still and you are the one moving. From that vantage point, the wire is exactly neutral. There is no net charge, and the very same push on you must be explained another way entirely. We call that other way the magnetic force. The identical physical event, the identical shove on the identical charge, is described as purely electric by one observer and as magnetic by another, and both are completely correct. Magnetism, in other words, is the bookkeeping that relativity forces upon us so that everyone, no matter how they are moving, agrees on what actually happens. It is electricity glimpsed from a moving frame. This is why the magnetism of your refrigerator magnet traces back to those tiny atomic loops of moving charge, and never to any separate magnetic substance. There is no separate magnetic substance. There are only electric charges, and the magnetism we feel is the consequence of those charges being in motion, woven into the fabric of space and time by relativity. And now the great asymmetry should feel positively haunting. If magnetism is merely electricity in motion, and electric charge isolates so freely into lonely positives and lonely negatives, then why, When we turn to the magnetic side of the very same unified phenomenon, does nature slam the door and refuse to give us a single isolated pole? The two faces are the same force. One face hands out lonely charges without hesitation. The other has never, not once, surrendered a lonely pole. That refusal, in a phenomenon we now understand to be fundamentally one and the same, is the deepest hint that something important is missing from our picture of the world. And this brings us to the object at the center of the whole mystery, a magnetic monopole. The word itself tells you what it would be. Mono meaning one, pole meaning magnetic pole. A magnetic monopole would be a single, isolated magnetic pole, all by itself, with no partner. Imagine, just for a moment, that you could reach into a magnet and pull out a pure north pole, a tiny particle that carries magnetic charge the same way an electron carries electric charge. It would be a place in space where magnetic field lines simply begin, spraying outward in all directions with no opposite pole anywhere to balance it. Or its mirror image, a pure south pole, a point where magnetic field lines all converge and end. That object, that lonely source or sink of magnetism, is the magnetic monopole. And in over 2 centuries of careful experiment, not a single confirmed example of one has ever been found. It is worth being very precise here, because this is where people get confused, and the confusion goes right to the core of the idea. The 2 poles of an ordinary bar magnet are not monopoles. I want to hammer this distinction home because it matters more than almost anything else in this story. When we casually say a magnet has a north pole and a south pole, we are describing the 2 ends of a dipole, a 2-poled object. Those ends are real, you can feel their forces, but neither one is an independent source of magnetism. They are bookends that cannot exist without each other, and without everything in between. A true magnetic monopole would be something categorically different. It would be a fundamental object, like a particle, whose magnetic field genuinely originates from that one point, with no hidden loop, no opposite face, no partner pole tucked away somewhere. The north pole of your refrigerator magnet is a feature of a larger 2-poled structure. A monopole would be magnetic charge itself, isolated and complete on its own, the magnetic twin of a single electron's electric charge. To really see the difference, think about what the field lines look like. Field lines are just a way of drawing the shape and direction of a field. For a single electric charge, say a lone positive charge, the field lines radiate straight outward in every direction, like the spikes of a sea urchin, or like sunlight streaming out from a point. They start at the charge and head off to infinity. For a negative charge, they point the other way, streaming inward from all directions and terminating on the charge. The charge is where the lines begin or end. Now look at the field lines of an ordinary bar magnet. They emerge from the North Pole, arc gracefully through the surrounding space, sweep around and dive back into the South Pole, and crucially, they continue through the inside of the magnet to close the loop. They never simply begin and never simply end. They always form complete closed curves. There is nowhere in or around an ordinary magnet where a field line truly starts from nothing or stops at nothing. The lines always loop back on themselves. A magnetic monopole would shatter that picture. Around a lone north monopole, the magnetic field lines would radiate straight outward in all directions, exactly like the electric field of a positive charge, beginning at that single point and never looping back. Around a lone south monopole, they would converge inward and terminate. For the very first time, a magnetic field line would have a true beginning or a true end. That is the physical signature of magnetic charge, and that is precisely what nature appears never to produce. Everywhere we look, magnetic field lines close into loops. The monopole would be the one exception, the one place where the loop is broken open and magnetism springs from a single source. If this asymmetry bothers you, you are in excellent company, because it bothered the very people who first wrote down the laws of electricity and magnetism in their full glory. In the 1860s, the Scottish physicist James Clerk Maxwell pulled together everything that was then known about electricity and magnetism into a compact set of equations. These equations, finalized around 1865, are among the crowning achievements of all of physics. They describe how electric and magnetic fields are created, how they interact, and how they ripple through space as light itself. Generations of scientists built on the discoveries of pioneers like Coulomb, who measured the force between charges, like Ørsted, who noticed a compass needle twitch near a current-carrying wire, like Ampere, who worked out how currents create magnetism, and like Faraday, who showed that changing magnetism creates electric current. Maxwell wove their work into a single, breathtaking framework. And when you lay those equations out, something jumps out at anyone paying attention. They are almost, but not quite, beautifully symmetric between electricity and magnetism. You do not need the mathematics to feel the shape of it. Picture 4 statements about how the universe works. One statement says that electric charge is a source of electric field, that electric field lines begin and end on electric charges. There are the lonely charges again, sitting right there in the law as legitimate sources. A second statement is the magnetic counterpart, and you would expect it to say the same thing for magnetism, that magnetic charge is a source of magnetic field. But it does not say that. Instead, the magnetic statement says something stark and lopsided. It says, in effect, that there is no magnetic charge at all. It declares that magnetic field lines never begin and never end, that they always form closed loops, that the total magnetism flowing out of any closed surface you can imagine is exactly zero, always, with no exceptions. Where the electric law proudly names a source, the magnetic law announces an absence. It is the equation of the missing monopole, written into the foundations of physics as a flat denial. The other 2 statements describe how the fields dance together, how a changing magnetic field stirs up an electric field, and a changing electric field, along with electric currents, stirs up a magnetic field. And in these 2, you can see the same near symmetry with the same conspicuous gap. Electric currents, the flow of electric charge, appear as a source of magnetic field. But there is no corresponding term for a flow of magnetic charge serving as a source of electric field, because, again, there is supposedly no magnetic charge to flow. So the equations come tantalizingly close to treating electricity and magnetism as perfect mirror images of one another, and then, in exactly the places where magnetic charge would appear, they fall silent. The structure practically begs for those missing terms to be filled in. The slots are there, waiting, shaped precisely to hold magnetic charge and magnetic current. They simply sit empty, because, in our universe, nobody has ever found anything to put in them. This is a profoundly strange situation, and I want you to sit with how strange it is. Maxwell's equations are not some rough sketch. They are one of the most precisely tested theories in the history of science, accurate across an astonishing range of scales. They correctly predict the behavior of light, radio waves, the workings of motors and generators, the glow of your screen. They are right about essentially everything we throw at them, and yet, baked into their very form is this glaring imbalance, an electric side that allows lone charges, and a magnetic side that forbids them. The equations work perfectly well with the magnetic charge set to 0. That is the universe we appear to live in. But mathematically, nothing in the structure of the theory demands that it be 0. You can write magnetic charge into the equations, you can give it a symbol and a place, and the whole framework remains perfectly consistent. It becomes, if anything, more elegant, more balanced, more symmetric. The only reason we leave those terms out is that we have never measured anything that would fill them. Think about what that means. We have a theory that would be more beautiful, more complete, and more symmetric if magnetic monopoles existed. And the theory has comfortable, well-shaped room for them. The single fact standing between us and that more symmetric universe is experimental. We have not found one. Not that the laws forbid it, not that it would break anything. Simply that so far the cupboard is bare. And in physics, when your most fundamental equations have a perfectly sensible slot for something that nature seems to refuse to provide, that is not a footnote. That is a flashing signal that something deep is going on, something we may not yet fully understand. There is a temptation, when faced with this absence, to jump to a comfortable conclusion. Maybe monopoles just do not exist. Maybe the universe is simply lopsided, and magnetism only ever comes in pairs because that is the way reality is, full stop. And that is a perfectly reasonable position to hold. But it is worth being very careful about what the evidence actually tells us and what it does not. The fact that we have never detected a magnetic monopole does not prove that monopoles cannot exist. Absence of detection is not the same as proof of impossibility. It is entirely possible that monopoles are real, but vanishingly rare, or so heavy that we cannot produce them, or hiding in regimes we have not yet learned to probe. We will see, as we go deeper, that some of our most ambitious theories of nature do not merely permit monopoles, they actively demand them. They say monopoles must exist. Which leaves us with a genuine tension between elegant theory, which says they should be there, and stubborn observation, which keeps coming up empty. For now, let us simply appreciate the puzzle in its full force, because the rest of this journey hangs on understanding it clearly. On one side, we have electric charge, which isolates freely, which we manipulate every second of every day, which appears openly in our deepest equations as a legitimate source. On the other side, we have magnetism, which we have never once managed to isolate into a single pole, which seems to arise entirely from loops of moving electric charge, and which appears in our equations only as a closed, sourceless, looping field. The two are intimately related, two threads of one electromagnetic tapestry, and yet they obey strikingly different rules about whether you can have one piece on its own. And the monopole sits right in the gap between them, a hypothetical object that would heal the asymmetry in a single stroke. If even one genuine magnetic monopole exists somewhere, then magnetic charge is real. The empty slots in Maxwell's equations get filled, and electricity and magnetism finally stand as true mirror images, each with its own isolated charges, each able to source its own field, each capable of flowing as a current. The whole structure of electromagnetism would snap into a symmetry so clean and so satisfying that physicists have spent the better part of a century convinced it simply must be how the universe really works at its deepest level, even if we have not yet caught the proof. So the question that opened this whole exploration deserves to be asked one more time, now that you can feel its weight. Why can you hold a single electric charge in isolation, but never a single magnetic pole? Why does cutting a magnet only ever produce more magnets, each as two-faced as the last? Is the universe genuinely, fundamentally lopsided, with magnetism forever doomed to arrive in pairs? Or is there, somewhere out there in the vastness of space, or buried in the extreme conditions of the early cosmos, a single isolated north or south pole waiting to be discovered, an object that would restore the lost symmetry and rewrite the textbooks the instant it is found? The strangest part of all is what happens when you take the monopole seriously, not as a curiosity, but as a real possibility, and follow the logic where it leads. Because it turns out that the existence of even one magnetic monopole anywhere in the entire universe would not just balance the equations of electromagnetism, It would force an explanation for one of the most basic and most mysterious facts about the world, a fact so familiar that we almost never stop to wonder about it. The fact that electric charge itself comes in fixed, identical, indivisible units. Every electron in the cosmos carries precisely the same charge as every other electron, to a precision that defies coincidence. Nobody has ever fully explained why, and the first person to realize that a lonely magnetic pole might hold the answer was a quiet, brilliant physicist whose insight, made in the early 1930s, tied this missing particle to the deepest grain of reality itself. Let us begin with a fact so ordinary that you have probably never once paused to find it remarkable. Every electron in the universe carries exactly the same electric charge. Not roughly the same, not close enough for practical purposes, exactly the same, to a precision so staggering that no measurement has ever found the slightest deviation. The electron in the screen you are looking at right now carries the identical charge as an electron at the center of a distant galaxy, as an electron that existed moments after the universe began, as an electron that will exist trillions of years from now. They are all, every single one of them, perfectly identical in this respect. And the proton, that heavyweight at the core of the atom, carries a charge that is exactly equal and opposite to the electrons, despite being almost 2,000 times more massive and built from entirely different ingredients. This precise matching is the reason atoms are electrically neutral, the reason ordinary matter does not fly apart or stick together in violent electrical chaos, the reason you can sit calmly in your chair instead of being torn apart by the imbalance of uncountable charges in your own body. Stop and consider how strange that uniformity actually is. In almost everything else in nature, properties come in a smooth, continuous spread. Stars come in a vast range of masses, blending one into the next. Raindrops come in every size. Mountains, waves, grains of sand all show endless variation. Yet electric charge stubbornly refuses to vary. It does not come in a smooth continuum of values. It comes in fixed, discrete packets, like coins of a single denomination. You can have 1 unit of charge, or 2, or 3, or none, but you can never have 1.5 units, or the square root of 2 units, or any odd fractional sliver in between. Charge is, to use the technical word, quantized. It is chunked. It is granular. It comes only in whole number multiples of a single fundamental amount, the charge carried by one electron. This is one of the most important and most precisely verified facts in all of physics. And here is the uncomfortable truth that lurks behind it. For a very long time, nobody had the faintest idea why. The discovery that charge comes in discrete units crept up on physics gradually. When the electron was first identified by J.J. Thomson in 1897, here was a particle that carried a definite, specific amount of negative charge. A little over a decade later, in a famous and elegant experiment, Robert Millikan measured that charge directly. He suspended tiny droplets of oil in an electric field, watching how they rose and fell as they picked up extra electrons. And what he found was telling. The charge on any given droplet was always a whole number multiple of one basic amount. A droplet might carry the charge of 1 electron, or 2, or 5, but never 1.5. The charges always came in clean integer steps of the same fundamental unit. It was as if nature had a smallest coin of electric charge, and every object in the universe could only ever hold a whole number of those coins, never a fraction. This left physicists in a peculiar position. They had a rock-solid experimental fact, charge quantization, and absolutely no explanation for it. Nothing in Maxwell's equations requires charge to come in discrete units. As far as the classical theory of electromagnetism is concerned, charge could perfectly well be a smooth, continuous quantity, taking any value at all. You could imagine a universe with charges of every conceivable fractional size, all blending into one another. Maxwell's equations would not blink. They would handle it without complaint. And yet, our universe pointedly does not do this. It insists, with iron discipline, on whole number multiples of a single quantum of charge. The theory permits a continuum, but reality delivers a ladder. Why? What law of nature reaches in and forbids all the in-between values, leaving only the clean integer rungs? For decades, this question simply hung in the air, unanswered, almost unasked. It was treated as a brute fact about the world, the kind of thing you note down and move past. And then, in 1931, a young British physicist named Paul Dirac approached the problem from a completely unexpected direction and arrived at one of the most astonishing connections in the history of theoretical physics. Dirac was already a legend in the making. He was famously quiet, almost painfully so, a man who spoke rarely and chose his words with mathematical economy, but whose mind moved through the deepest structures of physics with breathtaking clarity. He had already revolutionized our understanding of the electron, writing down an equation that combined quantum mechanics with the theory of relativity, and, in doing so, predicting the existence of antimatter before anyone had ever seen it. Dirac trusted mathematical beauty the way other people trust their senses. He believed that if an idea was elegant enough, nature was likely to have used it. And in 1931, he turned that instinct loose on the question of the magnetic monopole. Here is the chain of reasoning he followed, and I will give it to you in physical terms, because the physical idea is what matters, not the machinery underneath it. Dirac asked a simple question. Suppose, just suppose, that a single magnetic monopole exists somewhere in the universe. Not a whole population of them, just one. What would quantum mechanics have to say about a charged particle, like an electron, moving in the magnetic field of that lone monopole? This was very much a quantum question, because by the early 1930s, the new quantum mechanics, developed by Schrödinger and others, had transformed how physicists thought about particles. An electron was no longer a tiny billiard ball following a definite path. It was described by a quantum wave, a spread-out, oscillating thing whose ripples encode the probability of finding the particle here or there. And waves have a special property that classical billiard balls do not. They have a phase, a kind of internal clock hand position that tells you where in its up and down cycle the wave currently sits. That phase turns out to be the key to the entire argument. When a charged particle travels through a magnetic field, the field gently winds up the phase of its quantum wave, twisting that internal clock hand around as the particle moves. Now imagine sending an electron on a journey that loops all the way around the lone monopole and returns to where it started. By the time it comes home, its quantum phase has been wound around by an amount that depends on how much magnetic charge the monopole carries and how much electric charge the electron carries. And here is the crucial demand that quantum mechanics imposes, the hinge on which everything turns. When the electron arrives back at its starting point, its quantum wave has to match up smoothly with itself. The wave must be single-valued, meaning it can only have one definite value at each point in space. You cannot have the wave be one thing and also, simultaneously, a contradictory thing at the very same place. That would be nonsense, like a clock reading both 3 o'clock and 7 o'clock at the same instant. So when the electron completes its loop, the total winding of its phase must come out to a whole number of complete turns, not 3 1/4 turns, not 2 1/2 turns, a whole number of full revolutions, so that the wave seamlessly rejoins itself. And right there, in that demand for consistency, the miracle happens. The requirement that the electron's quantum wave close up smoothly after circling the monopole forces a strict relationship between the electric charge of the electron and the magnetic charge of the monopole. The two cannot take just any values independently. They are locked together. The product of the electric charge and the magnetic charge must equal a whole number times a fundamental constant of nature. Turn that relationship around and you get the result that stunned the physics world. If even a single magnetic monopole exists anywhere in the universe, carrying some fixed amount of magnetic charge, then every electric charge everywhere must come in discrete, quantized units. The mere existence of one lonely magnetic pole would force all electric charge across the entire cosmos to be chunked into precise whole number multiples of a basic unit. Take a moment to absorb what Dirac had done, because it is genuinely one of the great moments of 20th century theoretical physics. He had taken two facts that seemed to have nothing whatsoever to do with each other. On one hand, the never-observed, almost mythical magnetic monopole. On the other hand, the rock-solid, daily measured fact that electric charge comes in discrete units. And he had shown that they were secretly, intimately connected. The existence of the first would automatically explain the second. The lonely magnetic pole that nobody had ever seen would, by its mere existence, account for the orderly quantization of every electric charge that everybody could measure. It was as if he had found a hidden thread running through the basement of reality, tying a phantom to a fact, and pulling on one made the other move. Let me put the logic the other way around, because both directions are worth feeling. We observe that electric charge is quantized. We have no other clean, compelling explanation for why this should be so. But if magnetic monopoles exist, then charge quantization is no longer a mystery at all. It becomes an inevitable consequence, a logical necessity. The universe would have no choice. So Dirac's argument turns the monopole from a mere curiosity, a way to prettify Maxwell's equations, into something far more compelling. It becomes a potential answer to a question we genuinely cannot otherwise answer. And in physics, a hypothesis that explains an unexplained fact carries enormous weight. It is one thing to say a particle would be nice to have for the sake of symmetry. It is another thing entirely to say that this particle, if it exists, would resolve one of the deepest puzzles about the structure of matter. There is a beautiful subtlety hidden in Dirac's result that deserves a closer look, because it reveals just how powerful the argument really is. Notice that the monopole does not need to be nearby for its effect to be felt. It does not need to be in your laboratory, or in your galaxy, or anywhere within reach. The argument requires only that one monopole exists somewhere, anywhere, in the entire universe at any time. Just one, in some remote corner of space, perhaps formed in the first instance after the universe began, and now drifting alone through the dark between galaxies, would be enough to force the quantization of every electric charge everywhere, including the charge of the electrons in your own body right now. The logical chain reaches across all of space and all of time. A single example anywhere is sufficient to constrain everything. That is an extraordinary kind of leverage for one undiscovered particle to wield. It is worth being honest about the strength and the limits of what this argument establishes, because good science means being clear about exactly what you have shown. Dirac proved that the existence of a monopole would explain charge quantization. He did not prove that monopoles must exist. The logic runs one way. Monopole implies quantization. It does not run backward in an airtight fashion. The fact that charge is quantized does not, all by itself, force the conclusion that a monopole is out there, because it remains possible that some entirely different mechanism, something we have not yet fully understood, is responsible for the quantization instead. So Dirac did not deliver a proof of the monopole's existence. What he delivered was something subtler and, in its way, more seductive. He showed that the monopole would be a remarkably economical explanation for something we badly need to explain. He gave physicists a powerful reason to want monopoles to be real, and an even more powerful reason to go looking for them. he transformed the search from an idle hunt for a symmetry-completing oddity into a quest that might unlock the basic grain of electric charge itself. Dirac himself was characteristically careful and characteristically bold at the same time. He recognized that he could not prove the monopole existed, but he also reasoned, in his understated way, that since the monopole would so beautifully explain charge quantization, and since nothing in the laws of physics forbade it, one would be surprised if nature had simply declined to make use of such an elegant possibility. He famously suggested that, given the theoretical appeal, it would be strange if monopoles did not exist somewhere in the universe. This was Dirac's deep faith in mathematical beauty as a guide to physical truth, the same faith that had led him to predict antimatter. To him, an idea this clean and this useful seemed too good for nature to waste. And that conviction, that monopoles ought to be real because they would tie up such a profound loose end, has echoed through theoretical physics ever since, motivating decades of searching and a great deal of further theory. Now, you might reasonably wonder whether this whole argument is some delicate special case, a clever trick that only works under just so conditions. It is not. One of the most striking features of Dirac's reasoning is how robust and general it is. It does not depend on the detailed inner workings of the monopole or the electron. It does not require any specific exotic theory. It flows almost entirely from two pillars that we have tested to extraordinary precision. The first is the basic structure of quantum mechanics, in particular, the demand that quantum waves be consistent and single-valued. The second is the basic structure of electromagnetism, the way magnetic fields wind the phase of charged particles. Combine those two well-established frameworks, drop a single monopole into the picture, and the quantization of charge tumbles out almost as a matter of logic. That is what gives the argument such staying power. It is not built on speculative sand. It is built on the bedrock of two of our most successful theories, and it shows that those two theories, taken together, already contain a hidden link between magnetic charge and the granularity of electric charge. This is also a good moment to widen the picture, because charge quantization runs even deeper than the electron and the proton. When physicists looked inside the proton and neutron, they discovered the quarks, the smaller particles from which those heavier particles are built. And the quarks carry charges that are fractions of the electron's charge, in tidy thirds. Some quarks carry 2/3 of the basic unit, others carry -1/3. At first glance, this might seem to break the clean pattern of whole number charges. But look closer, and the quantization is, if anything, even more striking. The quarks still come in fixed, discrete amounts. They simply use a finer denomination of the same currency, steps of 1/3 rather than steps of 1. And nature arranges that quarks only ever combine into larger particles whose total charge comes out to a whole number of electron units. 3 quarks bundle together to make a proton with a charge of exactly +1, or a neutron with a charge of exactly 0. The fractional charges always assemble into whole number totals in anything we can isolate. So the great fact stands undisturbed and even reinforced. Charge, at every level we have probed, is rigidly quantized. The pattern is universal, and a universal pattern this exact cries out for a universal explanation, which is exactly the kind of thing Dirac's monopole could provide. Let me try to give you a feeling for just how good the experimental verification of charge quantization really is, so you appreciate what any explanation has to account for. Physicists have searched with enormous care for any particle carrying a charge that does not fit the expected pattern, any stray fractional charge floating free, any tiny mismatch between the magnitude of the proton's charge and the electron's. They have tested whether the proton and electron charges are truly equal and opposite by looking for the faint electrical effects that would appear in bulk matter if they were even minutely different. And every test comes back the same. The charges match to a precision of many decimal places. No free fractional charges have ever been confirmed. The quantization holds to a degree that would be almost absurd to attribute to mere coincidence. Whatever explains charge quantization must explain why it is this perfect, this exact, this universal. Dirac's monopole offers precisely that kind of clean, all-or-nothing answer. The relationship it imposes is not approximate. It is exact, a strict whole number locking of electric and magnetic charge, which is exactly the flavor of explanation the perfection of charge quantization seems to demand. There is one more dimension to Dirac's insight that elevates it from clever to profound, and it concerns the relationship between electricity and magnetism that we explored earlier. Recall the great asymmetry. Electric charge isolates freely and appears openly in our equations as a source. Magnetic charge has never been seen and sits as an empty slot. Dirac's argument does something remarkable to that picture. It shows that the two missing pieces are not independent. The existence of isolated magnetic charge and the quantization of electric charge are bound together as two faces of one underlying structure. If you fill in the empty magnetic slot with even a single monopole, you simultaneously explain why the electric charges that fill the other slots come in neat, identical packets. The asymmetry and the quantization, two separate seeming features of the world, turn out to be deeply entangled. Heal one, and you illuminate the other. That kind of unexpected connection, where solving one puzzle hands you the solution to a second, is exactly the signature physicists have learned to recognize as a sign that they are touching something true. So where does this leave us in the larger story? We began with a stubborn asymmetry, the fact that magnetism only ever comes in inseparable pairs, while electricity isolates freely. We saw that filling the empty magnetic slots in Maxwell's equations with a real magnetic charge would restore a gorgeous symmetry to the laws of electromagnetism. And now, with Dirac, we have discovered that the payoff is far richer than mere aesthetic balance. A single magnetic monopole anywhere in the universe would not only complete the symmetry of electromagnetism, it would explain why electric charge comes in discrete, identical units, solving a mystery that has no other clean solution. The monopole has grown, in our hands, from a curiosity into a kind of master key, an object whose existence would unlock two of the deepest features of the physical world at once. And yet, for all its theoretical beauty, for all the explanatory power Dirac packed into it, the monopole remained exactly what it had always been, undetected, unconfirmed. A magnificent idea with no corresponding object on any laboratory bench. Dirac's argument made physicists hungry to find one, and search they did, with increasing ingenuity decade after decade. But the equations being beautiful and the explanation being elegant are not the same as the particle being real. Nature is under no obligation to make our theories pretty, so the central tension of our whole exploration only sharpened. Theory now pointed, more insistently than ever, toward the monopole's existence. Observation continued to offer nothing but silence. For a while, the monopole sat in this strange limbo, theoretically motivated but experimentally absent, neither confirmed nor ruled out. And it might have stayed there indefinitely, a tantalizing maybe, if not for a dramatic development that arrived decades later, when physicists began trying to unify the fundamental forces of nature at the highest imaginable energies. Because when they built those grand new theories, the ones that attempt to weave the separate forces of the universe into a single fabric, they discovered something they had not been looking for, and could not easily ignore. The monopole was not merely allowed by these theories, it came roaring out of them, unbidden and unavoidable, predicted to exist with a definiteness that left no room for maybe. And, even more startling, these theories told us roughly what such a monopole would weigh. The answer was a number so enormous, so far beyond anything we could ever hope to manufacture, that it would reshape the entire question of where and how we might ever hope to find one. By the middle of the 20th century, physicists had a powerful but oddly fragmented picture of how the universe works. They had identified 4 fundamental forces, 4 basic ways that things in nature push and pull on one another. There was gravity, the gentle, universal attraction that holds planets in orbit and gives weight to your body. There was electromagnetism, the force we have been exploring, responsible for light, electricity, magnetism, and the chemistry of every atom. And there were 2 forces that operate only deep inside the nucleus of the atom, hidden from everyday experience. The strong nuclear force, which glues quarks together into protons and neutrons and binds those into atomic nuclei. And the weak nuclear force, responsible for certain kinds of radioactive decay, the slow transformation of one element into another. 4 forces, each with its own strength, its own rules, its own range of action. They seemed like 4 separate facts about the world, 4 independent characters in the story of reality. But physicists are restless creatures, and they had learned a profound lesson from history. Forces that appear separate have a habit of turning out to be the same thing, viewed from different angles. Recall what Maxwell had done in the 1860s. Before him, electricity and magnetism were considered 2 distinct phenomena. You studied electricity over here, magnetism over there, and never the twain shall meet. Maxwell showed they were 2 aspects of a single, unified electromagnetic force. The lightning and the compass needle were revealed as kin. This unification was not just tidy bookkeeping, it was a genuine deepening of understanding, and it predicted entirely new things, like the existence of electromagnetic waves traveling at the speed of light, which is to say, light itself. The lesson stuck. When you find 2 forces, look for the deeper unity beneath them. And so the dream took hold. If electricity and magnetism could be unified, why not the others? Why not weave all the forces of nature into a single, elegant framework, a single mathematical structure from which all 4 would emerge as different faces of one underlying reality? The first great success along this path came in the 1960s and 70s, when physicists managed to unify electromagnetism with the weak nuclear force. At the energies of everyday life, these 2 forces look nothing alike. Electromagnetism reaches across vast distances, while the weak force acts only over a span smaller than an atomic nucleus. They seem utterly different. But the new theory showed that at sufficiently high energies, the kind of energies that existed in the blazing first moments of the universe, these 2 forces merge into a single, unified force, sometimes called the electroweak force. As the universe cooled from its initial inferno, that unified force split, like a single substance freezing into distinct crystals, into the separate electromagnetic and weak forces we observe today. This was a triumph. It was confirmed by experiment. It showed that the dream of unification was not mere wishful thinking. Nature really did seem to organize its forces into deeper unities that reveal themselves at high enough energies. Buoyed by this success, theorists set their sights higher. If electromagnetism and the weak force could be unified, perhaps the strong nuclear force could be brought into the fold as well. The theories that attempt this grander synthesis, merging the strong force together with the already unified electro-weak force, are known as grand unified theories. The idea is breathtaking in its ambition. At energies almost unimaginably higher than anything we encounter, energies that existed only in the very earliest instant of the universe. All three of these forces, the strong, the weak, and the electromagnetic, would melt together into a single, grand, unified force. Three of the four fundamental forces of nature revealed as one. The differences we observe between them today would be nothing more than the frozen remnants of a unity that reigned when the cosmos was young and hot beyond comprehension. Gravity, the fourth force, remains stubbornly outside even these grand schemes, requiring a still deeper theory that no one has yet completed. But unifying 3 out of 4 would be an extraordinary achievement, a profound step toward understanding the architecture of reality. These grand unified theories were not just philosophical poetry. They were detailed mathematical structures, and, like any good theory, they made predictions. And here is where our story takes a dramatic turn, where the monopole comes surging back into the picture from an entirely unexpected direction. In 1974, two physicists working independently, Gerard 't Hooft and Alexander Polyakov, made a discovery that sent a jolt through the physics community. They were studying the mathematical consequences of these unified theories, exploring what kinds of objects such theories would naturally contain. And what they found was that grand unified theories do not merely permit the existence of magnetic monopoles, they demand it. The monopole is not an optional extra you can choose to include or leave out. It falls out of the mathematics automatically, an unavoidable consequence of the theory's very structure. Let me try to convey why this happens, in physical terms, because it is genuinely beautiful. When the single grand unified force splits apart as the universe cools into the separate forces we know, that splitting does not happen in a perfectly uniform way everywhere at once. Think of how water freezes into ice. As a body of water cools and crystallizes, the ice does not form as one flawless, perfect crystal. Different regions begin to freeze independently, each settling into its own orientation, its own pattern. Where these mismatched regions meet, you get defects, flaws in the crystal where the patterns fail to line up smoothly. Now picture something similar happening to the fabric of physical law itself in the early universe. As the unified force fractured into its separate pieces, different regions of space settled into their new configurations independently. And where those regions met, where the patterns could not be smoothly reconciled, the theory predicts that knots, twists, stable defects would form in the fields that fill space. And these defects, these unavoidable snags in the freezing of the forces, are precisely magnetic monopoles. The monopole is a knot in the fabric of unified physics, a place where the field cannot untangle itself, frozen into existence as the forces went their separate ways. This was a stunning development, and it deserves to be appreciated for what it accomplished. Dirac had shown that monopoles were possible and that they would beautifully explain charge quantization. But Dirac's argument did not tell you whether monopoles actually existed, nor did it tell you anything about their properties, like their mass. The grand unified theories went much further. They said monopoles must exist, that the very structure of unified physics guarantees their formation in the early universe. And, even more remarkably, they pinned down roughly what such a monopole would weigh. Because the monopole is a knot tied at the scale where the forces unify, its mass is set by the energy of that unification scale. And that energy is colossal, almost beyond comprehension. How heavy would a grand unified monopole be? The number is so large it strains the imagination. These theories predict a monopole with a mass somewhere in the neighborhood of 10 to the 16th times the mass of a proton. Let me try to make that staggering figure mean something. A single grand unified monopole would weigh roughly as much as a tiny grain of dust or a single living cell, something you could almost glimpse under a good microscope. Now, that might not sound like much. A dust grain is tiny. But remember, This is the mass of a single fundamental particle, an object that would otherwise behave like an elementary point. To pack the mass of an entire dust grain into one particle is to create something fantastically, absurdly heavy by the standards of particle physics. An ordinary proton is already a substantial particle by subatomic measures, and this monopole would outweigh it by a factor of 10,000 trillion. It would be the heaviest single object ever predicted to behave as a fundamental particle, a speck carrying the mass of a dust grain, all concentrated into one knotted point in the fields of nature. This enormous mass has a devastating consequence for our hopes of ever manufacturing one in a laboratory, and to understand why, we need to recall one of the deepest principles in physics, the equivalence of mass and energy. Mass and energy are two forms of the same thing, related by the most famous equation in science, which tells us that a given amount of mass corresponds to a certain amount of energy, and the other way around. This means that to create a particle of a particular mass, you must concentrate at least that much energy into a tiny region. This is exactly how particle accelerators work. They smash particles together at tremendous speeds, concentrating enormous energies into a vanishingly small point, and from that concentrated energy, new particles can materialize. The heavier the particle you want to create, the more energy you must pack into the collision. To make a heavy particle, you need a violent enough smash. And here is the crushing problem. The energy required to create a grand unified monopole, an energy corresponding to the mass of a dust grain concentrated in one particle, is so vast that it dwarfs anything we can produce by an almost laughable margin. Consider the Large Hadron Collider, the most powerful particle accelerator humanity has ever built. A ring buried beneath the border of two countries, 27 kilometers around, in which protons are whipped to nearly the speed of light and slammed together with breathtaking force. The Large Hadron Collider is a monument to human ingenuity, the pinnacle of our ability to concentrate energy. And yet, to create a grand unified monopole, you would need a collider not modestly more powerful than this one, but something like 1 trillion times more powerful, and then 1 trillion times more powerful again, and you would still be far short. The energies involved are not just beyond our current technology, they are beyond any technology we can realistically imagine. Energies that existed naturally only in the very first fraction of a second after the universe began, when everything was unimaginably hot and dense. We cannot make these monopoles. The energy scale required is the energy scale of the early universe itself, conditions we can never recreate on Earth. So if grand unified theories are correct, and if monopoles really are this heavy, then we will never build one. The only place such monopoles could ever have been created is in the early universe, in those first searing instants when the cosmos itself reached the grand unification energy. And this realization seemed at first like wonderful news. The theory predicted monopoles, predicted they would form in the early universe, and explained why we cannot make them ourselves. The pieces fit together. But this very success led physicists straight into a crisis, one of the strangest and most instructive problems in the history of cosmology. Because if monopoles really did form in the hot early universe, the theories predicted that they should have formed in absolutely staggering numbers, and that creates a catastrophic mismatch with the universe we actually observe. Let us walk through how this crisis unfolds, because it is a genuinely beautiful piece of reasoning, and its resolution is one of the great stories of modern physics. In the standard picture of the early universe, the cosmos began incredibly hot and dense, and has been expanding and cooling ever since. At the very beginning, in the first slivers of time, the temperature was high enough that all three forces were unified. As the universe expanded and cooled, it passed through the grand unification energy, the temperature at which the unified force splits into the separate forces. And it was precisely at this moment of splitting, this cosmic freezing, that the monopoles would have formed, as knots and defects in the fields, exactly as 't Hooft and Polyakov had described. Now, how many would form? The theory gives an estimate based on a simple and unavoidable principle. The defects form when different regions of space, freezing independently, fail to line up with one another. And the size of these independent regions is limited by how far any influence can travel in the available time, which is limited by the speed of light. In the extraordinarily young universe, almost no time had passed, so the regions that could communicate and coordinate with each other were absurdly small. This means space was carved up into a vast number of tiny independent patches, each freezing on its own, each potentially producing a monopole at its boundaries with its neighbours. Run the numbers, and the prediction is overwhelming. The early universe should have produced monopoles in such profusion that they would be roughly as common as protons and neutrons. The cosmos should be absolutely flooded with them, swimming in a sea of these incredibly heavy magnetic particles. And now you can see the catastrophe taking shape. Each monopole is staggeringly heavy, carrying the mass of a dust grain. If the universe were filled with monopoles in numbers anywhere close to the number of ordinary particles, the total mass tied up in those monopoles would be so immense that it would utterly dominate the cosmos. The gravitational consequences would be ruinous. The universe would be vastly heavier than anything we observe. Calculations show that with this many monopoles, the universe would be so dense that it would have recollapsed upon itself almost immediately after forming, or it would look nothing whatsoever like the universe we actually see, with its galaxies and stars spread thin across vast, mostly empty space. The predicted abundance of monopoles and the observed structure of the cosmos are wildly, fatally incompatible. This glaring contradiction came to be known as the monopole problem. The theories that so elegantly predicted monopoles also predicted far, far too many of them. So many that they should have wrecked the universe before it ever had a chance to become what it is. This was a serious crisis. On one hand, grand unified theories were attractive and successful in many respects, offering a compelling vision of unified forces. On the other hand, they seemed to predict a universe drowning in monopoles, a prediction in flat contradiction with reality. Something had to give. Either the grand unified theories were simply wrong, or there was some piece of the early universe story that physicists were missing, some mechanism that could have dramatically reduced the number of monopoles, sweeping the cosmos nearly clean of them. And it was in grappling with this very problem, among others, that one of the most transformative ideas in all of cosmology was born. In 1980, the physicist Alan Guth proposed a radical new idea about what happened in the earliest moments of the universe, an idea now known as cosmic inflation. The original motivation for inflation went beyond the monopole problem alone, addressing several puzzles about why the universe looks the way it does. But the monopole problem was very much among the difficulties that inflation so elegantly resolved, and it offers a beautiful illustration of how the idea works. Guth's proposal was this. In the very first instant after the universe began, before it settled into the steady expansion we observe today, there was a brief, almost violently dramatic episode of expansion. For an unimaginably tiny fraction of a second, the universe did not merely expand, it ballooned outward at a phenomenal accelerating rate, doubling in size again and again and again in rapid succession, blowing up by an enormous factor in almost no time at all. A region of space smaller than a single atom was stretched, in this fleeting burst, to something larger than the entire observable universe is today. This is inflation, a colossal exponential swelling of space itself in the first moments of creation. Now consider what this furious expansion would do to the monopoles. Suppose monopoles formed before, or right at the start of, this inflationary burst. The theory says they would have been produced in great numbers, packed relatively densely through space. But then inflation kicks in, and space stretches by an astronomical factor. The monopoles, riding along with the expanding space, are flung apart from one another with extraordinary speed. Where there had been many monopoles crowded into a small volume, inflation spreads them across an enormous, newly inflated volume. The density of monopoles, the number you would find in any given region, plummets. It is diluted to a tiny fraction of what it was, thinned out so drastically that monopoles become spectacularly rare. Picture a small drop of ink in a glass of water. Then imagine that glass suddenly expanding to the size of an ocean. The ink, once concentrated, is now spread so thinly that you could search vast stretches of water and never encounter a single molecule of it. Inflation does the same thing to monopoles. It takes a universe that was choking on them and stretches it out so violently that afterward you might have to search a volume larger than everything we can see just to find one. This is the elegant resolution of the monopole problem. The monopoles may well have formed exactly as grand unified theories predict, but cosmic inflation, by blowing up the universe by such an immense factor, would have diluted those primordial monopoles to almost nothing. After inflation, the expected number of monopoles within the entire observable universe might be just a handful, or even less than one. The catastrophe vanishes, not because the monopoles never existed, but because they were scattered so thinly across the inflated vastness of space that they no longer threaten to wreck the cosmos, and no longer guarantee we should easily find one. Inflation turns a fatal embarrassment into a quiet triumph. The same idea that explains so many other features of our universe also sweeps away the flood of monopoles, leaving behind a cosmos in which monopoles are not forbidden, but simply profoundly rare. It is worth pausing to appreciate the subtlety and the honesty of this situation. Inflation does not say monopoles do not exist. It says they may have formed and then been diluted to extreme scarcity. This is a crucial distinction. The grand unified monopole, if these theories are on the right track, is real, was created, and is out there somewhere. An incredibly heavy relic of the universe's first instant, but spread so thinly through space that encountering one would be a matter of extraordinary luck. The theory does not promise that monopoles are absent. It explains why, even if they are abundant in the absolute sense across the entire, perhaps infinite universe, they would be vanishingly uncommon within the patch of the cosmos we can actually observe and search. This also reframes the question of why we have not found a monopole. There is a tempting but mistaken line of thought that goes like this: we have searched and never found a monopole, therefore monopoles do not exist. But the grand unified picture, combined with inflation, shows exactly why this reasoning is too hasty. If monopoles are this heavy and this rare, then the absence of detection is precisely what you would expect, even if monopoles are perfectly real. We cannot make them because the energies are beyond us. And we have almost no chance of stumbling across a primordial one because inflation diluted them to extreme scarcity. The failure to find a monopole in this light does not count as evidence against their existence. It is fully consistent with their being real but rare. Non-detection does not prove impossibility. This is a recurring and important theme. The universe can contain things we have very good theoretical reasons to expect, and which we nonetheless cannot easily find, precisely because the same physics that predicts them also explains their scarcity. There is something almost poetic in how these ideas interlock. We set out, a little while ago, seeking to unify the forces of nature, a quest driven by the beauty of bringing separate things together under one framework. That quest predicted the monopole as an unavoidable consequence. The prediction then created a crisis, a universe that should have been ruined by an overabundance of monopoles. And the resolution of that crisis came from inflation, an idea that not only saved the monopole-bearing theories, but also explained a whole host of other deep features of the cosmos. Each step led naturally to the next, theory generating prediction, prediction generating crisis, crisis generating a still deeper theory. This is how physics actually advances, not in tidy, isolated leaps, but in this churning, interconnected way, where solving one problem reveals another, and the search for resolution drives us toward ever more profound understanding. And it is important to be clear-eyed about the status of all this. Grand unified theories, as compelling as they are, have not been confirmed. They remain attractive, well-motivated proposals, but the direct experimental evidence that would establish them is still missing, in part because the energies involved are so far beyond our reach. Some of their specific predictions, such as the eventual decay of the proton, have been searched for and not yet observed, placing constraints on which versions of these theories might be correct. So when we say grand unified theories predict heavy monopoles, we are describing what these particular theories imply, not a confirmed fact about nature. It remains entirely possible that the true theory of unified forces differs from current proposals, perhaps predicting monopoles with different masses, or under different conditions, or through different mechanisms. The honest position is that we have powerful theoretical reasons to expect monopoles, multiple independent lines of argument, all pointing toward their existence, and we have a coherent explanation for why they would be so hard to find. What we lack is the one thing that would settle everything, an actual monopole, detected and confirmed. This is precisely what makes the monopole such a tantalizing target. The theoretical case has only grown stronger over the decades. Dirac showed they would explain charge quantization. Grand unified theories showed they should exist as an unavoidable consequence of force unification, and told us roughly how heavy they would be. Inflation explained why, despite all this, they would be so rare that their absence from our experiments is no surprise at all. Every layer of theory has strengthened the expectation that monopoles are real, while simultaneously explaining why we have not found one. It is a remarkable situation, a particle that our best ideas about the universe insist should exist, and which those same ideas predict we would almost never encounter. But almost never is not never. Even if primordial monopoles are spread thin across the inflated immensity of the cosmos, the universe is unimaginably large, and the laws of chance leave room for a stray monopole to drift, even now, through the space around us, perhaps even through the Earth, a heavy relic of the first instant of creation, a frozen knot in the fields of nature, wandering alone through the dark. And if even one such monopole exists within reach, the question becomes how we might possibly catch it. How do you detect a single, fantastically heavy, fantastically rare particle that may pass through your equipment once in a lifetime, if ever? Physicists, undaunted by the long odds, have devised remarkably clever ways to try. They have buried detectors deep underground, flown instruments high above the Earth, and watched patiently for the unmistakable signature of a lone magnetic pole passing by. And in the course of this hunt, they have also had to learn to distinguish the true, fundamental monopole they seek from a family of clever imposters, objects that mimic the monopole's behavior inside certain exotic materials, and which have, more than once, made headlines that needed careful reading. So now we arrive at the hunt itself, the long, patient, sometimes heartbreaking effort to actually catch a magnetic monopole in the act of existing. And before we follow the hunters into their underground laboratories and out to the edges of the atmosphere, it is worth appreciating just how peculiar this quarry is, because the strangeness of the monopole shapes the entire strategy of the search. We are looking for an object that, if the grand unified theories are right, is fantastically heavy, carrying the mass of a dust grain in a single particle. We are looking for something that, thanks to cosmic inflation, may be so rare that only a handful exist within the entire observable universe. And we are looking for something that, by its very nature, would do something no ordinary particle can do. It would carry magnetic charge, a lone north or a lone south, the very thing that Maxwell's equations, in their standard form, declare impossible. This combination of properties, immense mass, extreme rarity, and a uniquely magnetic signature, makes the monopole one of the most challenging, and one of the most distinctive targets in all of experimental physics. The good news, if you can call it that, is that a genuine monopole would announce itself in ways that almost nothing else could mimic. Think back to what makes a monopole special. It is a source of magnetic field, a place where field lines truly begin or end. This means that if a monopole moves, it does something exotic. Just as a moving electric charge creates a magnetic field, a moving magnetic charge would create an electric field, and it would interact with matter in characteristic ways. A monopole passing through a material would leave a trail, depositing energy along its path in a manner subtly but measurably different from any ordinary particle. And, most beautifully of all, a monopole passing through a loop of wire would do something that Dirac's own physics predicts with crystalline clarity. It would induce a permanent, lasting change in the electric current flowing in that loop, a step change that simply does not happen for any conventional particle. This last property became the basis for one of the most famous and most poignant experiments in the entire history of the monopole search. To understand why, we need to recall a piece of basic electromagnetism. When an ordinary magnet, a dipole, passes through a loop of wire, it induces a current in that wire, but the effect is temporary. As the North Pole approaches, current flows one way. As the South Pole follows behind, the current reverses. The net effect, after the whole dipole has passed through, is zero. The current rises and falls and returns to where it started, because the two poles, being inseparable, always cancel each other's influence in the end. But now imagine a single monopole, a lone North Pole, with no South Pole trailing behind it, passing through the loop. There is no second pole to reverse the effect. The monopole induces a current that simply switches to a new steady level and stays there. The loop is left carrying a different, permanent current than before. This is the unmistakable signature of magnetic charge, a clean, irreversible step in the current of a wire loop, a jump that no ordinary particle and no ordinary dipole could ever produce. If you could build a sufficiently sensitive loop and watch it patiently, a passing monopole would leave behind this distinctive fingerprint. This is exactly what the physicist Blas Cabrera set out to detect at Stanford. He built a device of exquisite sensitivity, a loop of superconducting wire cooled to extraordinarily low temperatures, in which an electric current could flow without any resistance at all and persist essentially forever. In such a superconducting loop, a permanent step in the current induced by a passing monopole would not fade away. It would lock in, recorded for as long as the apparatus kept running. Cabrera carefully shielded his detector and set it to watch, day after day, for the telltale jump that would signal a monopole sailing through. It was an elegant experiment, beautifully designed to catch the one signature that a true fundamental monopole and almost nothing else could produce. And then, on the night of February 14th, 1982, on Valentine's Day, something extraordinary appeared in his data. While Cabrera was away, his detector recorded a single, sharp, clean event. A step in the current of exactly the size that a passing monopole would produce. Not approximately the right size, almost precisely the magnitude that Dirac's relationship predicted for a single magnetic charge. It was, on the face of it, the dream signal, the event that monopole hunters had been waiting decades to see. Cabrera returned to find that his instrument had registered just the kind of jump a lone magnetic pole would leave behind. The news rippled through the physics community with electric excitement. Had a magnetic monopole, that long-sought relic of the early universe, finally passed through a human-made detector and left its unmistakable mark? The single event was tantalizing, almost too perfect, and it carried with it the weight of half a century of theoretical anticipation, from Dirac's elegant argument to the grand unified predictions. But this is where the discipline of science shows its true character, and where the story takes its bittersweet turn. A single event, however perfect, is not enough. Science demands repeatability. A genuine discovery of this magnitude must be confirmed, seen again, reproduced by the same detector and by others. One event could be a monopole, but it could also be some subtle glitch, a mechanical disturbance, an electrical hiccup, a stray vibration that happened to mimic the expected signal. The only way to know for certain was to see another one. And so the wait began. Cabrera kept his detector running. He and others built larger, more sensitive versions, with bigger loops to catch more of the sky's potential monopoles. The physics community watched and waited for a second event to confirm the first. And it never came. Not from Cabrera's improved detectors, not from the larger experiments that followed, not from anyone, anywhere, in all the years since. The Valentine's Day event stands to this day as a solitary, unconfirmed, deeply tantalizing blip, almost certainly some unexplained artifact rather than a true monopole, precisely because nothing like it was ever seen again. It remains one of the great what-ifs of modern physics, a single, perfect signal that the universe stubbornly refused to repeat. The lesson of the Valentine's Day event is profound, and it cuts to the heart of how science protects itself from error. An extraordinary claim requires extraordinary evidence, and a single unrepeatable event, no matter how beautiful, cannot establish a discovery of this importance. The honest conclusion was not that a monopole had been found, but that something had been recorded which could not be confirmed, and therefore could not be claimed. This restraint, this refusal to declare victory on the strength of one perfect-looking signal, is not timidity. It is the very thing that makes scientific knowledge trustworthy. And so the search continued, undeterred, with physicists devising ever more varied and ingenious ways to catch the elusive particle. The strategies for detecting monopoles fall into a few broad families, each exploiting a different aspect of what a monopole would do. The induction approach, the one Cabrera pioneered, watches for the permanent current step in a superconducting loop. It has the great virtue of being almost uniquely sensitive to magnetic charge specifically, but it requires exquisite, delicate apparatus and can only watch a relatively small area at a time. A second family of approaches watches for the trail a monopole would leave as it plows through matter. Because a monopole interacts with the material it passes through, depositing energy in a distinctive way, detectors made of materials that record the passage of charged particles can be tuned to look for the particular signature a monopole would leave, a track that stands out from the ordinary debris of cosmic rays and radioactive decay. These detectors can be built large, watching big volumes of material, increasing the odds of catching a passing monopole. This second strategy is where some of the most ambitious modern searches come in, and they take advantage of structures built for other purposes as well as instruments designed specifically for the hunt. Consider the challenge. If primordial monopoles exist and drift through space, some of them might pass through the Earth and through any detector we happen to have running. But they would be incredibly rare, perhaps crossing a given detector once in many years, if ever. To have any realistic chance, you need either a very large detector or a very long observation time, or both. And it helps enormously to place your detector somewhere shielded from the relentless rain of ordinary cosmic particles that constantly bombard the surface of the Earth, because those particles create a confusing background that could mask or mimic a monopole signal. This is why so many of the great particle detectors are buried deep underground, beneath mountains or in old mines, using the rock above as a shield to filter out the ordinary cosmic clutter, leaving only the rarest and most penetrating particles to reach the instruments below. One of the most remarkable monopole hunting instruments is not buried in a mine, but frozen into the ice at the bottom of the world. The Ice Cube Observatory, located at the South Pole in Antarctica, is a detector of staggering scale. It consists of thousands of sensitive light detectors lowered deep into holes drilled into the Antarctic ice, instrumenting an entire cubic kilometre of that ancient, crystal-clear ice. IceCube was built primarily to detect neutrinos, those ghostly, nearly massless particles that stream through the universe. But its enormous volume and its sensitivity to faint flashes of light make it a powerful tool for hunting monopoles as well. A monopole passing through the deep ice would, according to theory, produce light along its path in a characteristic way, and with a full cubic kilometre of ice, watched by thousands of detectors, IceCube can search an enormous volume for the passage of these rare particles. The idea that we might catch a relic of the universe's first instant by watching for a flash of light in the ice at the South Pole is one of the more beautiful images in all of experimental physics. At the other end of the spectrum, rather than waiting for primordial monopoles to drift in from space, some physicists try to create monopoles directly, despite the daunting energy requirements we discussed earlier. To understand both the hope and the difficulty here, recall that the staggering mass of the grand unified monopole was set by the staggering energy scale at which all three forces unify. But unification is not the only way a monopole can arise. Different theories break their symmetries at different energies, and some propose intermediate stages, lesser unifications, that occur at far lower energies than the full grand unified scale. A monopole, born from one of those lighter stages, would be correspondingly lighter, and a lighter monopole means a less impossible energy required to make one. It is a long shot, but it is not an impossibility. And an outright impossibility is the only thing that ever truly halts a determined physicist. So, at the Large Hadron Collider, where protons are smashed together at the highest energies humanity can achieve, a dedicated experiment called the modal experiment was installed, specifically to search for monopoles, among other exotic particles. There is a subtlety in how a collision could even make one. A monopole cannot simply appear alone, because that would create magnetic charge out of nothing, and the universe keeps strict books. Instead, the pure energy of a collision would have to materialize a monopole and an anti-monopole together, a lone north and a lone south, born as a matched pair, conserving the overall balance even as each individual particle carries an isolated charge. There is a further twist that makes the calculation maddening. Dirac's own relationship implies that magnetic charge, if it exists, must be enormous compared to electric charge, which means a monopole would couple to the electromagnetic field ferociously strongly. That ferocity wrecks the usual mathematical tools physicists rely on to predict how often a particle will be produced, leaving us genuinely uncertain whether a collider could make monopoles, even if they are light enough in principle. The modal experiment sidesteps this uncertainty with a clever, almost old-fashioned strategy. It surrounds one of the collision points with sheets of specialized plastic, and with trapping material designed to catch a monopole rather than merely glimpse it in flight. A monopole, being magnetically charged and heavy, would bind tightly to the nuclei of that material and come to rest, lodged in place. Then, long after the collisions, scientists pass the trapping material slowly through an extremely sensitive magnetometer, the very kind of superconducting loop Cabrera pioneered. If a monopole is embedded inside, it betrays itself by leaving that same permanent, irreversible step in the current as the sample glides through. So the modal experiment watches patiently, not because it expects to find the heavy, grand, unified monopole, whose mass is utterly beyond reach, but because it might catch a lighter cousin if such a thing exists, and because a possibility left unchecked is no answer at all. There have also been searches in the most unexpected places. Physicists have examined ancient rock and deep-sea sediments, reasoning that if monopoles have been drifting through the Earth for billions of years, some might have become trapped in materials, leaving traces that could be detected by sensitive instruments today. They have passed samples of various materials through superconducting detectors, looking for any trapped monopole that might reveal itself. They have searched in moon rocks and meteorites. They have looked for the indirect effects monopoles might have on astrophysical objects, reasoning that monopoles caught inside stars or other bodies might produce subtle, observable consequences. Across all of these searches, spanning decades, employing a dazzling variety of techniques, watching underground and underwater, and in the ice, and at the highest energies we can produce, the result has been steadfastly, stubbornly the same. No confirmed detection. Not one fundamental magnetic monopole has ever been reliably found. The Valentine's Day event remains the closest anyone has come, and it stands alone and unconfirmed. There is also a wonderfully indirect way to hunt for monopoles, one that does not require catching a single one at all, and it relies on listening to what the entire galaxy is quietly telling us. Our Milky Way is threaded through with a vast, gentle magnetic field stretching across tens of thousands of light years, generated and sustained over cosmic time by the churning motion of charged gas within it. That galactic magnetic field has been there, in roughly its present strength, for a very long time. And here is the key insight, first worked out by the physicist Eugene Parker around 1970. A magnetic monopole, dropped into a magnetic field, does not just sit there, it gets pushed. Just as an electric field accelerates an electric charge, a magnetic field accelerates a magnetic charge, hauling the monopole along the field lines and dumping energy into its motion. And that energy has to come from somewhere. It is drained directly out of the galactic magnetic field itself. Now follow the logic, because it is beautifully simple. If the galaxy was swarming with monopoles, every one of them would be siphoning energy out of the magnetic field as it was flung along the field lines. With enough monopoles, they would bleed the field dry faster than the slow churning of the galaxy could rebuild it, and the galactic magnetic field would have collapsed long ago. But it has not collapsed. It is still here, still strong, still doing its quiet work across the spiral arms. The simple fact that our galaxy retains its magnetic field places a hard ceiling on how many monopoles can possibly be drifting through it. There cannot be very many, or the field could not survive. This upper limit on the cosmic flux of monopoles is known, fittingly, as the Parker bound, and it is one of the most elegant constraints in all of astrophysics. We learn something profound about a particle nobody has ever caught simply by noticing that the galaxy's magnetism is still switched on. What makes the Parker bound so satisfying is how perfectly it dovetails with everything inflation already told us. Inflation predicted that primordial monopoles would be diluted to extreme scarcity, spread so thin we might never meet one. The Parker bound, arriving from a completely different direction with completely different reasoning, agrees. It independently confirms that monopoles, if they are out there at all, must be extraordinarily rare, rare enough to leave the galaxy's magnetic field intact. Two unrelated arguments, one from the physics of the early universe and one from the magnetism of our galaxy today, converge on the very same verdict. And once again, notice precisely what that verdict is. Not that monopoles are absent, only that they are scarce. The constraint tells us there cannot be many drifting through our galaxy. It does not and cannot tell us there are none. There is one more property a grand unified monopole might possess, and it is so startling that it sounds like something out of a fever dream, yet it follows directly from the theories that predict the monopole in the first place. A monopole, according to work done in the early 1980s, by the physicists Curtis Callan and Valery Rubikoff, might be able to make ordinary matter fall apart. Not by smashing it, not by burning it, but simply by being near it. Recall that grand unified theories predict the proton, that supposedly eternal building block at the heart of every atom, is not truly stable, that over almost incomprehensibly long timescales, it should very occasionally decay into lighter particles. In ordinary circumstances, this process is so fantastically slow that we have never once observed it. But the mathematics suggests that the intense, tangled fields right at the core of a monopole could act as a catalyst, dramatically speeding the proton's decay, coaxing a proton that wandered too close to disintegrate almost instantly into a spray of lighter particles. This is called the Callan-Rubikoff effect, and its consequences are staggering to contemplate. Think about what it would mean for a monopole to drift through ordinary matter while carrying this ability. As it travels, it would leave behind not just a faint trail of deposited energy, but a wake of shattered protons, a string of induced decays marking its path like footprints. A single monopole crossing a large detector could trigger a sequence of these catalyzed decays, each one releasing a burst of energy and particles, producing a signature far louder and far more distinctive than the monopole's passage alone would create. This turns the catalysis from a curiosity into a powerful detection strategy. Some of the great underground experiments watch precisely for this, for the telltale chain of proton decays that a passing monopole might leave in its wake, a signal that almost nothing else in nature could counterfeit. And there is a deeper resonance here, a thread that ties this whole story together. Recall that the decay of the proton is itself one of the signature predictions of grand unified theories, a prediction physicists have searched for directly in enormous tanks of water buried deep underground without yet seeing it. The monopole and proton decay are not separate ideas. They spring from the same theoretical soil, two consequences of the same dream of unifying the forces. So, a monopole that catalyzes proton decay would be a single object embodying two of the boldest predictions of unified physics at once, a wandering knot in the fields of nature with the power to unmake the very matter it drifts through. Whether such a thing truly exists remains unknown, but the mere fact that our best theories can conjure an object this strange and connect it so tightly to the stability of the atoms in your own body shows just how much would be riding on finding even one. And yet, every so often over the years, headlines have appeared announcing that magnetic monopoles had been discovered, sometimes in language so confident that it seemed the great search was finally over. These announcements were not frauds, and they were not mistakes in the ordinary sense. They were reporting something genuinely real and genuinely fascinating. But they were describing something subtly, crucially different from the fundamental monopole we have been chasing throughout this whole story. And understanding that difference is essential, because it goes right to the heart of what we actually mean by a magnetic monopole. And it is one of the most commonly misunderstood points in all of this physics. What these announcements were describing were objects sometimes called emergent monopoles, or monopole-like quasiparticles, found inside certain exotic materials, most famously in a class of crystals known as spin ice. To understand what these are, and why they are not the real thing, we need to think carefully about the difference between a fundamental particle and an emergent phenomenon. A fundamental particle, like an electron, is one of the basic building blocks of reality. It is not made of anything smaller, as far as we know. An emergent phenomenon, by contrast, is a pattern of behavior that arises from the collective arrangement of many ordinary components, a behavior that the individual pieces do not have on their own, but that the group, organized in just the right way, can display together. Consider spin ice. It is a real, solid crystal made of perfectly ordinary atoms, in which the magnetic properties of the atoms are arranged in a special, frustrated pattern. Inside this material, under the right conditions, the collective behavior of countless tiny atomic magnets can organize itself in such a way that in certain spots within the crystal, the magnetism behaves as though there were an isolated North Pole, and in other spots, as though there were an isolated South Pole. These spots, these localized patterns in the collective magnetism of the material, behave in many ways like monopoles. They can move through the crystal, they attract and repel one another, they carry what looks, from the inside of the material, like an isolated magnetic charge. And they are genuinely useful and genuinely interesting, opening windows into the physics of complex materials and the strange ways that collective behavior can mimic fundamental particles. The discovery of these emergent monopoles in spin ice was a real and significant achievement in the physics of materials. But here is the all-important distinction. These emergent monopoles are not fundamental particles. They are not new building blocks of nature. They exist only inside the special material, as patterns in the collective behavior of ordinary atoms. They are, in a sense, illusions of magnetic charge, conjured by the clever arrangement of countless ordinary two-poled atomic magnets. They cannot be removed from the crystal and held in your hand as isolated objects. They have no existence outside the material that gives rise to them. And crucially, they do not change the fundamental picture of electromagnetism at all. They do not fill the empty slots in Maxwell's equations. They do not represent a true magnetic charge in the vacuum of space. They do not explain charge quantization the way Dirac's fundamental monopole would. They are a beautiful and instructive mimicry, a way that ordinary matter can be coaxed into imitating the behavior of a monopole, but they are emphatically not the fundamental, free, isolated magnetic charge that Dirac and the grand unified theories envisioned. The analogy I find most helpful is this. Imagine a stadium full of people doing a wave, where each person stands up and sits down in sequence so that a ripple appears to travel around the stadium. The wave is real. You can see it move. You can measure its speed. But the wave is not a thing in itself, not a substance that exists independently of the people. It is a pattern in the collective behavior of the crowd. No single person is the wave. You cannot extract the wave from the stadium and carry it home. The emergent monopole in spin ice is like that wave. It is a real, observable, well-defined pattern, but it is a pattern in the collective behavior of ordinary atoms, not a fundamental object that exists on its own. The fundamental monopole we have been seeking would be like one of the individual people, a genuine independent entity, not a pattern emerging from the arrangement of others. This distinction matters enormously, and it is why physicists, when these emergent monopoles were discovered, were careful in their more measured statements to specify exactly what had and had not been found. What had been found was a fascinating emergent phenomenon, monopole-like behavior in a special material. What had not been found, what remained as elusive as ever, was a fundamental magnetic monopole, a true isolated magnetic charge existing freely in nature, the kind that would rewrite electromagnetism and explain the quantization of charge. The headlines sometimes blurred this distinction, understandably, because the emergent monopoles are genuinely monopole-like and genuinely remarkable. But the careful, honest statement is clear. The emergent monopoles of spin ice are a triumph of materials physics and a beautiful illustration of how collective behavior can mimic fundamental phenomena. They are not, and do not claim to be, the fundamental monopole that our deepest theories predict and that our great searches continue to seek. So where does all of this leave us? After more than 2 centuries of studying magnetism, after Dirac's stunning argument connecting monopoles to charge quantization, after the grand unified theories that predict monopoles as an unavoidable consequence of unifying the forces, after inflation's elegant explanation for why they would be so rare, and after decades of ingenious searches buried in ice and rock and conducted at the highest energies we can muster, the situation can be stated with simple honesty. No confirmed fundamental magnetic monopole has ever been detected. The empty slots in Maxwell's equations remain empty. The great asymmetry between electricity and magnetism, the one we started with, the fact that you can isolate a single electric charge but never a single magnetic pole, still stands, unbroken, as far as direct observation can tell. But it is absolutely vital to understand what this absence does and does not mean, because this is where careful thinking separates real understanding from lazy conclusion. The failure to find a monopole does not prove that monopoles cannot exist. This point cannot be overstated. We have powerful theoretical reasons, multiple independent lines of argument, all pointing toward the monopole's existence. Dirac's argument shows that monopoles would explain a deep mystery. Grand unified theories predict that they must form, and inflation explains precisely why, even if they are real and were created in abundance, they would now be so rare that we would almost never encounter one. The very same physics that predicts monopoles also predicts that they would be extraordinarily difficult to find. So the non-detection of monopoles is entirely consistent with their being real but rare. Real but too heavy to produce. Real but spread so thin across the inflated vastness of space that we might search for generations and never cross paths with one. Absence of evidence in this carefully reasoned case is very far from evidence of absence. This is one of the most important habits of mind in all of science, and the monopole illustrates it perfectly. There is a world of difference between saying we have not found something and saying that something does not exist. The first is a statement about the limits of our search. The second is a far stronger claim about the nature of reality, a claim that the evidence simply does not support. We have not found a monopole, that is true, but the universe is vast, almost beyond comprehension. Our searches have probed only a minuscule fraction of it, and our best theories give us excellent reasons to keep looking. The monopole remains, in the most precise terms, undetected but not disproven, theoretically motivated but experimentally unconfirmed, a particle that hovers in the fascinating space between prediction and observation. And this is precisely what makes the monopole such an extraordinary prize, and why physicists continue to hunt for it with undiminished determination. Because consider what would happen if even a single fundamental monopole were found, if just one genuine isolated magnetic charge were detected and confirmed. The consequences would be nothing short of transformative. First, it would instantly restore the lost symmetry of electromagnetism. The empty magnetic slots in Maxwell's equations would be filled. Magnetic charge would become as real as electric charge. Electricity and magnetism would finally stand as true mirror images of one another, each with its own isolated charges, each able to serve as a source of its field. The lopsided, asymmetric laws we have lived with for over a century would snap into a clean, balanced, gorgeous symmetry. The great asymmetry that opened our entire exploration would be healed in a single stroke. Second, and even more profoundly, finding a monopole would immediately explain why electric charge is quantized. Recall Dirac's argument. The mere existence of one monopole anywhere forces all electric charge to come in discrete units. So the discovery of a real monopole would not just complete electromagnetism, it would resolve one of the deepest and most precisely verified mysteries about the structure of matter. The question of why every electron in the universe carries exactly the same charge. Why charge comes in clean, identical, indivisible packets. A mystery that has no other clean explanation would be solved by a single detection. The orderly granularity of electric charge, that strange and beautiful fact, would finally have its reason. Third, finding a monopole would give us a precious, direct window into physics at the very highest energies, the grand unification scale. Energies we can never hope to reach with any accelerator we could build. If the monopole turned out to be one of the heavy, grand unified variety, its very existence would be powerful evidence that the forces of nature really do unify at those colossal energies, confirming a vision of unified physics that we currently can only theorize about. A single monopole would be a messenger from the first instant of the universe, a fossil from the moment the forces separated, carrying information about physics far beyond anything we can recreate. It would be a direct, tangible link to the deepest layers of reality and the earliest moments of time. Think about the full sweep of what we have traced. We began with something as simple and familiar as a magnet on a refrigerator, and the innocent observation that you can never cut it to isolate a single pole. We followed that observation down into the atom, to the loops of moving charge that make magnetism, and saw why the two poles are inseparable faces of one circulating thing. We confronted the great asymmetry written into the very foundations of electromagnetism, the empty slots in Maxwell's equations where magnetic charge could sit. We met Dirac, who showed that filling even one of those slots anywhere in the cosmos would explain why electric charge comes in fixed units. We watched the grand unified theories predict monopoles as an unavoidable consequence of unifying the forces, and tell us they would be staggeringly heavy. We saw the monopole problem threaten to drown the universe, and watched cosmic inflation dilute the flood to near nothing, explaining the monopole's profound rarity. And finally, we joined the hunt, through underground caverns and Antarctic ice and the highest energy collisions we can produce, learning to tell the true fundamental monopole apart from its emergent imitators, and confronting the honest fact that, so far, the search has come up empty. The magnetic monopole, then, is a perfect emblem of how physics works at its most profound. It is an object motivated by symmetry, demanded by some of our deepest theories, capable of explaining a fundamental mystery about charge, and yet held just beyond the reach of confirmed detection by its likely enormous mass and its uncertain, inflation-thinned production history. It sits at the crossroads of electromagnetism, particle physics, and cosmology, tying together the behavior of a humble bar magnet, the granularity of electric charge, the unification of the forces, and the first instant of the universe. Whether or not it is ever found, the pursuit of the monopole has already taught us extraordinary things about the structure of physical law and the architecture of the cosmos. And the search goes on, in laboratories around the world and beneath the ice at the bottom of the earth, watching, waiting, for the day a single lone magnetic pole might finally reveal itself. Because if it does, if even one is ever found, the textbooks will be rewritten in an instant, and our understanding of electromagnetism, of charge, and of the deep symmetries of nature will never be the same again.